You know how large language models, those incredibly smart AIs like GPT-4o and Gemini, can sometimes confidently tell you something that just isn't quite right?
Oh, absolutely. It's like they've read every book up to, say, last year,
Yeah.
but ask about yesterday's news.
Exactly. Or some really obscure fact, and they just kind of make things up, what people call hallucinating. It's pretty frustrating when you need the real answer.
It really is. It points to a fundamental limit, doesn't it?
Yeah.
Their knowledge is, well, static, frozen at the point their training ended, and the world keeps moving.
Right. So today we're doing a deep dive into something designed to tackle exactly that. It's a new framework called MMSearch-R1.
hmm
Imagine an AI that not only gets your question, but intelligently figures out, hey, do I need to check the live internet for this one?
And that's the key bit, the intelligence to decide. It's not just blindly searching every time.
Exactly. This isn't about just, bolting on a search engine. It's about teaching the AI to be a smart researcher itself, to know when it doesn't know.
That ability to recognize its own limits is, I think, a really significant step forward.
So our mission today is to unpack this. We'll look at the core problem MMSearch-R1 addresses, dig into the clever ways it learns to handle real-world info, and then look at the results,
Yeah.
all following the kind of structure you'd see in the actual research paper. Ready to get into it?
Let's do it.
Okay, so let's start right there, the problem. What exactly is the core limitation with current LMMs that MMSearch-R1 is trying to fix?
It really comes down to that static knowledge base we mentioned. They're trained on these massive data sets, huge amounts of text and images, but that data has a cutoff date.
So anything new, anything that happened after that date?
They struggle, especially with what researchers call long-tail information. Think really recent events, breaking news, or super niche, specific knowledge that just wasn't common enough to be in the original training data.
And that's when the hallucinations kick in.
Precisely. When faced with something outside that internal knowledge, they tend to generate confidently wrong answers. And that really hurts their reliability,
Yeah.
especially for tasks needing factual accuracy.
Can you give us a concrete example, something that would really trip up a standard LMM?
Sure. Imagine asking about the specific date NASA's Viper moon rover project got canceled in 2024.
Okay.
That's a very recent specific fact. Without the ability to do a real-time search, the LMM would likely either guess, maybe pull an old, irrelevant date, or just say it doesn't know, but it might also just make up a date.
Right, because that info wasn't baked in from the start. So people have obviously tried to fix this before MMSearch-R1. What about existing solutions like retrieval-augmented generation or RAG?
Yeah, RAG is a common approach. The basic idea is to give the AI access to an external knowledge source, like a database or a specific set of documents.
Like a curated library it can check.
Yeah. Kind of, yeah. It retrieves relevant snippets from that external source before generating its answer and incorporates that information. It definitely helps expand the knowledge it can access.
But it's not perfect, right? What are the limitations there?
A big one is the workflow. It's often this rigid retrieve then generate process, always. Meaning it might search even when it doesn't need to. We call that over-retrieving, which wastes time and computational resources.
Ah, okay.
And critically, RG systems often assume the answer is actually in that external knowledge base they're given access to. But for really dynamic real-world stuff, especially very recent events, that might not be true. The information might only be on the live web.
Okay, so RE has its limits. What about these other things? Prompt-engineered agents, how do they try to solve it?
Those are more about giving the AI very detailed instructions, basically, using carefully crafted prompts to guide a large model through steps like search the web for X, read the results, summarize, then search for Y.
Like a recipe for searching.
Exactly. It tells the model how to use a search engine, step by step.
Sounds kind of smart. What's the catch?
The catch is that the AI itself isn't really learning from this process. Its core parameters, its underlying understanding, aren't being optimized. It's just following instructions.
So it doesn't get better at searching over time or adapting to weird search results?
Not fundamentally, no. It doesn't develop that intrinsic skill of knowing how to interact effectively with search tools or how to handle the messy, unpredictable nature of the real internet.
Okay, that sets the stage nicely for MMSearch-R1. You said its approach is different because it uses end-to-end reinforcement learning.
Okay.
And it's the first to do this for on-demand, multi-turn search on the real internet.
That's the claim, and it seems to hold up. The on-demand part is really crucial
Why is that?
because it means the model isn't just searching all the time, like some RG setups. It learns to make a judgment call. MMSearch-R1 specifically trains the LMM to develop 3 key abilities related to search.
Okay, what are they?
First, knowing when to search. Basically, recognizing the edge of its own knowledge. Second, knowing what to search for, how to formulate a good, precise query. And third, knowing how to use the search results reasoning over that retrieved information to actually answer the question properly.
So it's learning to be an actual researcher, not just a lookup tool.
Exactly. It's developing genuine search skills.
All right, let's dig into how they actually built this thing. Section 2, the framework, starting with the brains. Group Relative Policy Optimization, or GRPO. Now, reinforcement learning, RL, is involved here. Can you give us the quick version of RL in this context?
Sure. Think of it like training a dog. The AI tries an action in this case, deciding whether to search, what query to use, or just answering. Based on the outcome, it gets a reward or a penalty. Over time, it learns which actions lead to good outcomes, like accurate answers.
Okay, so trial and error with feedback. And this GRPO algorithm, what's special about it?
It's a specific type of RL algorithm, a variation of something well-known called PPO. What's really neat about GRPO, the way they use it here, is how it estimates the baseline for rewards.
How so?
Instead of needing a whole separate component to judge the value of actions, it estimates this directly from a group of reward signals obtained during training. It makes the whole training process significantly more efficient computationally.
So learning from the group's performance makes it faster and less resource hungry.
Exactly. It's a clever optimization. And, importantly, this whole setup is designed to let the model interact directly with the real internet during training, what they call the rollout process. That's where it actually tries out these multi-step searches.
That direct interaction sounds key for learning real-world messiness.
It is. That's how it learns to adapt its search strategy on the fly based on what it finds, just like a person would.
Okay, makes sense. Now what about the tools? You can't search without tools. What does MMSearch-R1 have in its toolkit? Especially for multimodal stuff, mixing images and text.
Right. You need the right tools. It has 2 main ones. First, an image search tool.
What does that do?
Its purpose is to help the model figure out what it's looking at if the visual content is unfamiliar. So you give it an image, it sends it off to an image search engine they use, SirPoppy, and gets back the top few visually similar web pages shown as thumbnails and titles.
So if it sees a weird landmark it doesn't recognize.
It can use the image search to get clues, like, oh, that's the Eiffel Tower. They also built in caching, so if it sees the same image URL again, it doesn't have to search again. Smart for efficiency.
Okay, image search for unfamiliar visuals. What's the second tool?
The text search tool. This is for when it needs factual information, like that Viper cancellation date.
And how does that work? It sounds a bit more complex.
It is. It's actually a pipeline of tools working together. First, the model generates a text query, like NASA Viper cancellation date 2024. That query goes to SirPoppy again, which returns the top 5 or so relevant web page URLs. Then, another tool, GeneReader, fetches the full content of those pages and cleans it up into readable text.
The whole web page? That sounds like a lot of text.
It can be, yeah. Which is why the final step is crucial. They use another powerful language model, specifically Qwen 332b, as a web page summarizer. It reads each fetched page and extracts just the concise, relevant bits related to the original question. This drastically cuts down the amount of text the main LMM has to process.
Ah, that's clever. Summarize first. So this whole chain relies on external APIs and services. How robust is it? Things can fail online.
That's a fair point. They put effort into robustness. They use multi-layer caching fast Redis for common stuff, bigger object storage for large parse pages to avoid redoing work, and they implemented distributed rate limiting to avoid overwhelming the external APIs.
And does it work? What's the failure rate?
According to their paper, it's actually quite low, around 0.2% failure for the end-to-end image search and about 1% for the text search pipeline, which, considering all the moving parts interacting with a live web, is pretty impressive.
Okay, remarkably low. So we have the brains, GRPO, and the tools, image text search. Now, the process. How does a query actually play out, this rollout with multi-turn, multimodal search?
Right, so for anything complex, the model doesn't just do one search and give up. It can engage in multiple rounds of interaction with the internet.
Iterative searching.
Exactly. And importantly, it's guided to reason about its steps. It actually outputs its thought process within special tags, like reason.reason, whenever it gets new information, like the initial question or the results from a search it just did.
So you can see it thinking, okay, I got this info, now I need that info, so I'll search for it.
Precisely. It makes the process more transparent. Then, based on its reasoning, It chooses its next action from a limited set.
What are the options?
It can decide to provide the final answer using answer.answer tags. Or it can decide it needs more info and call the image search tool using search. Or call the text search tool by generating a query within tags like text search query goes, here text search.
And whatever it finds comes back to it.
Yes, all the retrieved info image search results, text summaries, is fed back to the model wrapped in information.information tags. This feeds into its next reasoning step, and this loop continues until it gives an answer or hits a preset limit on the number of turns.
Let's revisit that Viper rover example. Walk us through the turns with these tags.
Okay, step 1, model gets the image and question, when was Viper canceled? It might output reason. The image shows the Viper rover, but doesn't contain the cancellation date. I need to search for this factual information. Reason text search, NASA Viper Moon rover project cancellation date, 2024 text search.
Makes sense. Then what?
Step 2, it gets back the search results, maybe a summary saying NASA canceled Viper on July 17, 2024. This comes back as information NASA canceled Viper on July 17, 2024 due to budget constraints.information.
Oh.
Step 3, the model sees this. It might output reason. The search results provide the specific cancellation date. Reason answer, NASA's Viper Moon rover project was canceled on July 17, 2024. Answer. And that's the final answer.
That's really clear how the reasoning and actions link up. What about that Spitfire example? Picture of the plane, question who designed it.
Right. Step 1, model gets image and question. It might reason, the image shows a Supermarine Spitfire. I recognize the aircraft, but the image doesn't state the designer. I need to perform a text search for this information. Reason text search. Who designed the Supermarine Spitfire text search?
So it recognized the plane, knew it needed text info, not image info.
Yeah,
Smart.
Exactly. Step 2, it gets back information. The Supermarine Spitfire was designed by R.J. Mitchell.information. Step 3, it reasons the search result directly answers the question about the designer. Reason answer. The Supermarine Spitfire was designed by R.J. Mitchell.answer. Done.
Fascinating. It really shows the intelligence in choosing the right action. Okay, but how does it learn to make these good choices? That brings us to the guidance. Reward modeling. This sounds critical for RL.
Absolutely critical. The reward model defines what good behavior looks like. It's the feedback signal that drives the learning. Here, it has two main parts.
Okay, part 1.
Part 1 is basically an accuracy score, but with a clever twist, a search penalty.
How does that work?
Simple. If the final answer is exactly right compared to the known ground truth, the accuracy score is 1, otherwise 0. But, and this is the key, if the model got the right answer by using any search tool, image or text, a small penalty factor, like 0.1, is applied to that score.
So it gets rewarded most if it gets the answer right without searching.
Exactly. It incentivizes the model to rely on its internal knowledge whenever possible. Only search when you really need to. This is how they bake in that on-demand search behavior. Use your own brain first.
Very clever. What's the second part of the reward?
The second part is simpler. A format score. This just checks if the model followed the rules during its interaction turns. Did it use the reason, search, answer tags correctly? It ensures the model learns to communicate its process clearly and consistently.
And these two scores are combined.
Yes, they're added together, but the accuracy score, with its penalty, is weighted much more heavily. Getting the right answer is still the main goal, but doing it efficiently matters too.
Right. Makes sense. Now, all this training needs the right fuel. Let's talk about the data. They created a whole new data set called Factual VQA, or FVQA. Why couldn't they just use existing VQA datasets?
Good question. Existing datasets, while great for general visual question answering, weren't really designed to train this specific on-demand search capability. FVQA was custom-built with 3 key criteria in mind.
Okay, criterion 1.
It needed a good mix of questions, some that the model should be able to answer from its internal knowledge, search-free, and others that absolutely require looking things up externally, search required.
And those search required ones.
They further broke those down. Some need visual knowledge, like identifying that Spitfire maybe if it wasn't common. Others need textual knowledge, like the Viper cancellation date. So a mix of reasons why search might be needed.
Okay, mix of search-no search and types of search needed. What's criterion 2?
The answers needed to be concise and unambiguous. Things like dates, names, specific facts. This makes it much easier to automatically check if the model's answer is correct during training. No fuzzy, open-ended answers.
Got it. Easy verification. And the third criterion.
Diversity. They wanted the data set to cover a wide range of knowledge categories. Arts, science, people, places, events, you name it. And also different difficulty levels. This helps ensure the model can generalize its learned skills to new, unseen questions.
So how did they actually build this diverse, balanced data set? They mentioned a semi-automated pipeline.
Yeah, it was quite involved. They started by automatically sampling thousands of visual concepts using metadata from Metacleap, making sure to get both common head concepts and rarer tail ones.
Yep.
Then, they used a powerful model like GPT-4o to generate lots of factual question-answer pairs based on these concepts, aiming for those concise answers. That formed the bulk of the automated data. They also pulled in some examples from another dataset focused on textual knowledge, InfoSeek. And importantly, they added manually written examples too to capture how real users might ask questions.
So a mix of automated generation and human input. What about that crucial search balancing part? How did they ensure the right mix of search-required versus search-free questions?
That was key. They used another AI model, actually a Quinn variant, as a classifier. They fed it all the generated questions and had it predict whether answering that question would likely require image search, text search, both, or no search at all.
Using AI to label the data for training another AI meta.
Exactly. This allowed them to create a final training set, about 5,000 samples, carefully balanced, with roughly 3,400 search-required examples and 1,600 search-free ones. This balance, as we'll see, is critical for teaching that efficient on-demand behavior.
And they also needed a separate, high-quality test set for evaluation, right?
Correct. They put together another 1,800 examples, which were either manually verified or fully human annotated, drawing from various sources, just to be absolutely sure they had a reliable benchmark for testing performance accurately.
Okay, problem defined, framework dissected, data built. Now for the payoff. Section 3, the findings. How did MMSearch-R1 actually perform in practice? Let's start with the setups. What was the base model they used?
They used Quinn 2.5 VL7B Instruct as the backbone model, a pretty capable 7 billion parameter multimodal model.
And training details?
Trained on that balanced FEQA trained dataset we just discussed. They used batches of 512 examples, let the model have up to 8 attempts or rollouts per example, with a maximum of 3 dialogue rounds and 2 search actions allowed per round.
Okay. And what did they test it against? Benchmarks and baselines?
They evaluated it on their own FEQA test set, which is in-domain, but also on several out-of-domain datasets like InfoSeek, MMSearch, Simple VQA, and Live VQA to really test generalization.
And the comparisons. Who are the competitors?
They compared it against some heavy hitters. GPT-4o, Gemini 2.5 Pro. Also against different versions of the base Quinn model itself, running in 2 modes. One mode was direct answer, just answer from internal knowledge, no search allowed.
Like a standard LMM.
Right. The other mode was a typical RAG workflow, where the model was forced to perform 2 search operations, image then text or text then text, before answering, regardless of whether it was needed.
Okay, so comparing against no search and always search. And how did they measure success? The metric.
Primarily accuracy, using GPT-4o as an automated judge to score the final answers. But they also heavily track the search ratio, or SR basically, what percentage of the time that the model actually choose to use a search tool compared to the maximum it was allowed. This measures efficiency.
All right, let's get to the results. Finding 1, superior performance and search efficiency. What did they find?
This is pretty striking. MMSearch-R1, the 7B model, consistently outperformed the REA baselines of the same size by an average of 3% in accuracy across all the test sets, both in-domain and out-of-domain.
So better answers. What about the efficiency?
That's where it really shines. It slashed the average search rate by almost 33%.
Wow, a third fewer searches.
Yeah, a huge reduction. It clearly shows the model learned to be much more selective and targeted in when it decided to search. It wasn't just searching blindly.
That's impressive for the same size model. How did it stack up against bigger models using the RVARIG approach?
This is also quite telling. The MMSearch-R1 7B model performed competitively with a RRAID-based Quinn 2.5 VL32B model.
Wait, the 7 billion parameter model kept up with the 32 billion parameter one?
Pretty much, yeah, in terms of accuracy.
Right.
But the key is it achieved this competitive accuracy while making way fewer search calls. It really underscores how much benefit you get from learning an adaptive search strategy versus just using a fixed brute force RF pipeline on a bigger model.
That's a huge point about learned efficiency. Okay, finding 2. Enhanced query generation and information summarization. What does this mean?
This means the benefits of the RL training went beyond just learning when to search. They tested the RL trained model even in a forced RAG setting, where it had to search every time.
Yeah.
Even then, it performed better than the original base model in the same forced RAG setting.
So even when forced to search, it searched better.
Exactly. It indicates the RL training also improved its core retrieval skills, formulating more effective, context-aware text queries to send to the search engine, and doing a better job of extracting the truly useful information from the potentially noisy search results and summaries it got back. It got better at the whole search process.
Interesting. Finding 3. Improved utilization of internal knowledge. This sounds like it relates back to that search penalty.
It does, absolutely.
Right.
They look closely at the model's behavior, specifically how often it got the answer right without needing to search at all.
And what was the trend?
A clear upward trend. The final RL-trained MMSearch-R1 model answered significantly more questions correctly, using only its internal knowledge compared to the base model before RL training.
So it really did learn to check its own brain first.
Yes, it demonstrated better recall and reasoning based purely on its parameters. It learned to trust its internal knowledge when appropriate, saving the external search tools for questions that genuinely required them, the new, the niche, the long-tail stuff.
Excellent. Finding 4. Higher data efficiency compared to supervised fine-tuning, SFT. SFT is the more traditional way of training, right?
Right. Supervised fine-tuning usually involves training the model on a large data set of input-output pairs, essentially showing it examples of correct search behavior.
So how did RL compare?
The RL-trained model consistently beat the SFT-trained model across all the tasks. And here's the kicker. It achieved this superior performance using only about half the amount of training data.
Half the data for better results. That's a big deal for training costs.
It really is. Roughly 5,000 samples for the RL training versus about 8,000 for the SFT comparison they did. Plus, the RL model's behavior seemed better aligned with the task needs, for instance. It naturally invoked search more often on datasets known to contain more recent or rare information, like MMSearch and LiveVQA.
Okay, last one. Finding 5. The crucial role of balanced data and search penalty. They did some tests to isolate these factors.
Yes, ablation studies. They tried training versions of the model without the search penalty in the reward or without using the carefully search-balanced dataset, meaning the training data wasn't a controlled mix of search-needed and search-not-needed questions.
And what happened when they removed those components?
The results were stark. In both cases, no penalty or unbalanced data. The model quickly learned to just overuse the search tool. The search ratio shot up towards 100%, meaning it basically searched almost every single time, regardless of need.
So it lost that efficiency, that on-demand aspect.
Completely. In contrast, the full MMSearch-R1 model, with the penalty and the balanced data, achieved similar overall final reward scores, meaning good accuracy, but maintained that much lower, stable, efficient search ratio. It proves that those two elements are the secret sauce for teaching selective, efficient, truly on-demand search.
So let's wrap this up. What's the big picture takeaway here?
I mean, MMSearch-R1 really looks like a significant step forward. It's about equipping these powerful multimodal models with genuine research skills for navigating the real, dynamic world of information.
Not just retrieving, but researching intelligently.
Exactly. Using reinforcement learning, that clever reward structure with the penalty and the purpose-built dataset, it teaches the AI to be smart about when and how it searches. On demand. Efficiently.
Which should mean fewer factual errors, fewer hallucinations, right? And better handling of up-to-the-minute information.
That's the promise, and the results seem to bear it out. It's a move towards more reliable and adaptable AI.
Of course, it's research, so there are always limitations or next steps, right?
Oh, for sure. The authors acknowledge challenges. For one, the performance still depends on the quality and stability of those external search tools, which can vary. That 1% failure rate for text search isn't zero.
True.
And the reward function, while clever, relies on an exact string match for accuracy. That works well for factual questions with single, precise answers. But it might struggle with more nuanced questions where answers aren't just right or wrong, but better or worse, or need interpretation.
Yeah, how do you reward understanding subtlety?
Right. Building more flexible reward systems that capture semantic meaning, not just exact matches, is definitely a key area for future work.
So looking ahead then, this work seems to lay some serious groundwork for AI agents that are much more interactive and adaptive.
I think so. As models get better at using tools like search to explore the real world, well, where does that lead?
Could we see AIs that don't just wait for our questions, but maybe anticipate what we need to know, or even conduct complex research projects mostly on their own?
It certainly opens up possibilities. Imagine an AI seamlessly integrating into how we find and process information, maybe acting as a research assistant that truly understands when to dig deeper. It does raise fascinating questions about how our relationship with knowledge and learning might evolve as these capabilities mature.
Definitely something to think about. A future where AI isn't just a know-it-all, but a learn-it-all, figuring things out alongside us. Thanks for walking us through this. That was a fantastic deep dive.
My pleasure. It's exciting work.